Hello, AP Chemistry. So we are looking at Unit 6, all right, Thermodynamics. So two big enduring understandings: changes in a substance's properties or change into a different substance requires an exchange of energy. And the energy exchanged in a chemical transformation is required to break and form bonds, right? Um, I will be a little repetitive. There's a couple of main key pieces that I want to make sure you have down. All right. So first thing, temperature changes in a system indicate energy changes. Right. So anytime we see the temperature go up, we know that an energy change is occurring. Right. Energy is the motion of the particles. Right. Kinetic energy, 1/2 mass times velocity squared. And if particles are moving faster, they are at a higher temperature. All right, so temperature is defined as the average kinetic energy of a substance, right? So as a liquid increases its temperature, its particles are moving faster. Now, energy changes in a system can be described as endothermic and exothermic processes, such as the heating or cooling of a substance, phase changes, or chemical transformations. It's very important that we feel comfortable with these two terms, endothermic and exothermic. And most of the time they make sense, but every now and then we kind of get ourselves tripped up when we're thinking about an application of them in a weird scenario. So let's just always remember, exothermic means that the heat or the energy, it leaves the system and it enters the surroundings. So if we can define a system and we can define the surroundings, if heat is moving from system to surroundings, that's going to be exothermic. All right. Now, if the heat is going from the surroundings into the system, that is endothermic. So anything that gains energy is endothermic. Anything that releases energy is exothermic. When we're thinking purely about heat exchange, heat always flows downhill, and we will see this in later slides. All right. So heat always moves from a hot source to a cold source. So if the system is hotter than its surroundings, it moves outward. And if the surroundings are hotter than the system, the heat moves inward. All right. Now let's think about these phase changes. To go from ice to water, we have to add energy. Well, adding energy is an endothermic process. So ice melting is endothermic. That's something that we don't always feel comfortable with. All right. Liquid water boiling is also endothermic. And again, we kind of get confused because you figure, well, the stove would be on to boil the water, and the stove is exothermic, but the water itself, defining the water as a system, it's endothermic when it boils. Now, when we remove energy, so when water from the gaseous phase condenses, that's exothermic. It releases energy. And when water freezes, that is also exothermic. So those are kind of like the tricky ones. It's the phase changes that I think trip people up, but just define the system and think about where the energy is flowing. Is going into the system, right? Which makes sense that ice needs to gain energy to become water to melt. All right, if it's a chemical reaction, we're going to be looking at these energy profiles, and we should feel pretty comfortable with this. If the energy of the reactants is less than the energy of the products, we have gained energy. This is endothermic. And if the energy is less, we have lost energy, exothermic. All right, so if we end up higher, endo. If we end up lower, exo. And we can write heat as a reactant. If heat is a reactant, it's going to be an endothermic reaction. It's going to be a reaction that absorbs that heat, and heat can be a product. All right, so a lot of combustion reactions, heat will be a product. So that would be an exothermic reaction. And instead of heat, we could write the amount of energy in kilojoules for either. And then we get this delta H. All right, delta H is the enthalpy change. Enthalpy looks at internal energy and work. You don't really have to worry about enthalpy. If you want to just think of it as heat, that's totally fine. Delta H, heat. If delta H is positive, that is endothermic. If delta H is negative, that is exothermic. This is a really important thing you want to have down. It will be developed further in Unit 9, which is applications of thermochemistry. So it goes a little further, but you want to feel comfortable with this. For me, I really found this year, I always know it, but every now and then I kind of forget. But the negative delta H, someone posted a meme, Will Smith looking through the binoculars, and he sees negative delta H, and he says, "That's hot." And that has really stuck in my head. So that's how I like now always make sure I know negative delta H, exothermic, always. All right, now the formation of a solution. So we dissolve things, and typically sometimes it gets a little warm, specifically like sodium hydroxide. If we ever make a solution of sodium hydroxide in the lab, that one will release a lot of heat. It'll get kind of warm. But then other solutions, like a cold pack, all right, it's dissolving ammonium chloride typically, or ammonium nitrate, excuse me. So a cold pack, you mix the two solutions in the pack, and it gets really cold. So mixing of solutions, it can be exothermic or endothermic. All right, it can go either way, and this process, it depends on the relative strengths of the intermolecular or in the interparticle interactions before and after the dissolution process. So we have two examples here. Two things have to happen. The solvent has to be separated, and the solute has to be separated. In both diagrams, those are both endothermic processes. We have to put energy in to separate the solvent. We have to put energy in to separate the solute. And then the separated particles mix together, and that is always an exothermic process. In the left, the separated particles forming the solution releases a lot of energy, so we end up with an overall exothermic process because our final product is lower in potential energy and in enthalpy than our initial reactants. In the endothermic process, it took more energy than was released, so overall it was endothermic. We actually had to absorb energy. All right, so again, 3 steps here. You gotta separate the solvent, you gotta separate the solute, and then you gotta allow them to mix. These first 2 steps, their delta H is always going to be positive. Separating the solvent, separating the solute, always going to require energy. Allowing them to mix is always going to release energy. All right. And typically, our delta H of solutions, typically it's very small. So even though it can be exothermic or endothermic, it's only ever going to occur if it's small, right? It's not going to occur if we ever get a really big number. It doesn't matter if it's endo or exothermic. It's only going to occur if it's small. So we have this chart. We can look at the delta H of separating the solvent, of separating the solute, and then of the solute-solvent interactions, and we can get an idea of what will happen, right? So if the amount of energy to separate is large for both, but then the amount of energy released is also large, we're probably going to get a small delta H, and so that solution will usually form. All right. If we get a mix of small and large, but it's important that one of them is large for the delta H1 or delta H2. So at least one of the pieces requires a lot of energy, whether it's the solute or the solvent. But overall, these solute-solvent interactions are really small, which typically occurs when we either have a polar with a nonpolar or vice versa. Typically, we get large delta H's for delta H3 when they're either both polar or both nonpolar. Anyway, the solution's most likely not going to form if we end up with a really large positive value for the delta H. All right, so that's these middle 2 scenarios. And the bottom one, let's say we have really small amounts of enthalpy for separating the solvent, small amount for separating the solute, and then a small negative value for the solute-solvent interaction. Well, again, we're most likely going to get that small positive or negative number, but a small solution will usually form. So solutions form when their enthalpy change is rather small. When it's too great, it's just thermodynamically not favorable, and we'll see what that phrase, thermodynamically not favorable, means in Unit 9, so you don't have to worry about it for right now. All right, so a physical or chemical process can be described with an energy diagram that shows the endothermic or exothermic nature of that process. All right, here I have a reaction that is really broken down step by step. We've seen this in the textbook. Enthalpy of the atomization of metal M, right? The ionization enthalpy of the atomization of X. So typically if it's something like chlorine, the bond energy has to be split in half. The sum of the ionization energies, the enthalpy change, right? All of these steps, but they all have a different enthalpy change associated with them, and they all kind of get added together. So here's an example of magnesium plus chlorine forming magnesium chloride. All right, it is not a simple process. It's got a lot of steps. So step one, the solid magnesium needs to be sublimated. It needs to be in the gaseous form, right? So that's going to require an input of energy. And the chlorine needs to be split apart. We need to break the bond. It's a Cl2 molecule. It needs to be two individual atoms. That's that atomization. That's more energy input, right? Endothermic. Then the magnesium, it needs to lose an electron, right? That's its first ionization energy. That's an input of energy. And it needs to lose a second electron, right? It needs to become Mg2+. So now we have twice looked at the ionization energy. First ionization, second ionization. Now, those are all of the endothermic parts of this reaction. Exothermically, well, chlorine, it's going to have an energy associated with gaining an electron. That's its electron affinity, right? So now we're going to have negative numbers, and then we're going to get the actual lattice energy, right? When the ionic bond forms between the magnesium 2+ and the 2Cl-, and so whatever that lattice energy is, that is also going to be negative. That's going to be exothermic, and that's where we kind of hit like the big payload, so to speak. But overall, right, even though we go through all of these steps, our net reaction, negative 642 kilojoules per mole. So even though we had some energy changes in the thousands at different points, overall, we're still not a huge energy change. All right, and negative 642 kilojoules per mole is actually quite large relative to other simpler reactions. But again, if we're ever going up on a potential energy or enthalpy scale, going up is always endothermic, coming down is always exothermic. So just keep that in mind. All right, and when we make really stable products, they should end up really low. So they release a lot of energy to release those really stable products. All right. That is breaking it down into all the steps. Typically, we'll just see one profile. Even this one is a little complicated because it has the intermediate, right? But we would have the activation energy. Wherever we start is the reactants. The products are on the other side of the path. So we've seen these profiles, all right? And here, products are lower than reactants, exothermic. All right, now, the particles in a warmer body have a greater average kinetic energy than those in a cooler body. All right, so whenever we're talking about an average temperature, not every particle has that exact speed, right? But the majority of them do, and that gives us our average, but we get some particles that are a little faster and some particles that are a little slower. All right, so typically when we have a cold sample, we get this pretty big exponential graph. Right? So if we have a cold sample, it kind of spikes and we get a high average around a lower energy. If we have a warmer sample, it's a flatter curve. All right, this should look like the flatten the curve graphs you've seen. All right, and there's the memes about learning about these in math class and thinking, when are we going to need them? But it comes up a lot in the AP curriculum. Even before this whole quarantine, they really love this graph because it shows you, if you pick a certain energy, and this could be activation energy, this could be whatever, but if you just pick a spot in the higher temperature graph, right, and these are Maxwell-Boltzmann distributions, at the higher temperature, more area, right, more area under the curve. For my calculus students, we're thinking about integration here, but more of those particles would meet that threshold kinetic energy. They would either have it or be greater, right? Nothing up to that energy counts, right? This whole space doesn't count. So the majority for here, it looks like about half of the particles have that temperature. Whereas if I look at my lower temperature sample, yeah, some of those particles have that amount of energy, but a very small fraction of it. All right, so literally a small fraction of the lower temperature sample has the same kinetic energy as half of the higher temperature sample. So it's a huge disparity when we think about the total number of particles at a certain energy for a higher temperature. All right, so again, Maxwell-Boltzmann distribution curves. Now, the particles in a warmer body have a greater average kinetic energy, and that just means their speed, right? So the hot air particles move much faster than the cold air particles. And since they move faster, they transfer more energy in every collision, whereas the cold air particles, they don't transfer a lot in those collisions. All right, now the collisions are important here. Collisions between particles in thermal contact can result in the transfer of energy. This process is called heat transfer, heat exchange, or transfer of heat as energy. So the idea is if you have a hot source and a cold source, they have to come in contact, right? So contact is a huge piece, but when they're in contact, the collisions from the hot source will be colliding into particles of the cold source. And so those collisions will transfer energy. The hot source will cool down. The cold source will increase in energy because it's going to be receiving energy from all these collisions, and it's going to become warm. Now, again, the important thing with heat, it flows downhill, right? So we always move from hot to cold. It flows downhill. So when they're in contact, right, and it's important that, surface area is a huge factor in how much contact we can have. The high energy collision will hit and it'll lose a little bit of its energy. Now, it doesn't lose it, it transfers it to the cooler side. So now it moves away, moving a little slower, but the blue particle, to represent the cooler substance, is colliding. It's receiving that energy in the collision. Now it's moving away a little faster. So the cold gets heated up, the hot gets cooled down, and they will meet at a spot where we call thermal equilibrium, right? They will spread out until they are both even. But this has to be, there has to be contact here, right? They have to be together. So a very common lab we do is we drop a hot piece of metal into a beaker of water, right? No thermal equilibrium could be reached while they're separate, right? While the hot piece of metal is not touching the water. But when you drop the hot piece of metal in, the hot piece of metal is vibrating and it is actually transferring energy in the collisions with the surface of the water. All right, so that's what's going on. Something I just want you to think about if you're watching this video, a hydro flask, all right, or any really good water bottle like that, a lot of them are vacuum sealed. So there's actually a thin gap between, there's an inner chamber and the outer chamber, and it's vacuum sealed. And the whole point of it being vacuum sealed is it has less particles, so there's no contact, right? The inner cylinder has no contact with the outer one, so heat exchange is not able to happen, right? Because those vibrations have nothing to transfer to. All right, even normal air, if something was sitting out and it was hot, it will transfer energy just to the air around it. So heat transfer will be kind of happening pretty much anywhere. But in a vacuum sealed like hydro flask, it's significantly minimized because there's just less stuff to gain that energy. All right, now the thermal equilibrium, again, very common lab, dropping a hot metal into the water. They will reach the same temperature. These are these questions where we do the energy lost. The negative of the energy lost is equal to the energy gained, right? A Q equals negative Q type problem. So here's our formula. Here's what I mean when I say Q. Q equals MC delta T, right? Q is the energy transferred, typically joules. It could be in kilojoules. They could be really goofy and put it into calories, which is totally fine. 1 calorie equals 4.18 joules. M is the mass, right? Typically it's of water if we're looking at a sample of water, but it could be the mass of the metal, it could be the mass of whatever substance we're looking at. C is the specific heat capacity, All right, every substance has its own unique specific heat capacity. And then delta T, it's temperature change. It is okay if we leave the temperatures in Kelvin or Celsius, right? Because they have the same intervals. Kelvin is just the Celsius temperature plus 273. But it is important for our delta T, it's always the final temperature minus the initial. All right, so it can be a negative number if the final temperature is lower than the initial temperature, all right, or it could be a positive number. So these are situations, labs we've done where we were using a coffee cup and the thermometer was inside of it and we were trying to record a temperature change. All right, so that's again, we're using the formula Q equals MC delta T. The heating of a cool body by a warmer body, it's important in these energy changes. Right? Now we get the first law of thermodynamics. The first law of thermodynamics states that energy is conserved in chemical and physical processes. All right, now this has a huge application because typically in a lab we typically lose energy, but we don't lose it. It's not destroyed. It's just converting to a different form, and oftentimes we lose energy just to the surroundings. All right, so it's very common. We're using those coffee cups. They work pretty well. In a high-tech lab, they would use what's called a bomb calorimeter, which reduces the energy loss to the surroundings even greater. But for the most part, any lab you're going to do in a high school laboratory, you're going to lose some energy. We could think of it as work potentially if it's creating a volume change in the surroundings, or just heat in general. But the simple thing here for the first law of thermodynamics, let's just think the energy before is the energy after, right? It's not, energy's never being gained, it's never being destroyed, it's being converted from form to form. All right, kinetic energy, heat, all of these things. So again, we don't create energy out of nowhere. We put energy in, we get some type of transition, the energy is now there. All right, now this is something interesting. The transfer of a given amount of thermal energy will not produce the same temperature change in equal masses of matter with differing specific heat capacities. All right, so here's our example. If we give a kilogram of gold and a kilogram of aluminum the same amount of energy, all right, the gold will heat up 7 times faster than the aluminum. All right, and that's because of their own specific heats. So the gold gains that energy very quickly relative to the aluminum, and the gold will also lose that energy very quickly. So there is this law. This is not in the AP chemistry at all, but I just felt the need to talk about it for a second. It's this law of Dulong and Petit, where they came up with this very complicated looking equation to come up with specific heat capacities. All right, there's a simpler approximation. You would do 3R, and R is the gas law constant, 3R divided by the molar mass. Right, that gives you a pretty close approximation for the specific heat of different metals. All right, really low specific heats mean that they gain the energy quickly. Higher specific heats means that they take a longer amount of time to gain. All right, a great example is water. Water has a high specific heat, 4.18. And so if you have a water balloon, you can put like a candle underneath it, and the candle will pull the heat away from the water, and the water balloon will not pop. All right, and if you've ever put your hand over a candle for a few seconds, it hurts. So it is a lot of energy being transferred, but the water is able to absorb it. Whereas something like lead would get pretty hot pretty quickly because of its specific heat. All right, now again, heating a system increases the energy of the system, while cooling a system decreases the energy of the system. We've already seen this in this review. All right, so again, just good to define the system and the surroundings and to remember heat flows downhill. All right, now the specific heat capacity of a substance and the molar heat capacity are both used in energy calculations. Specific heat units, it's typically joules per gram degree Celsius, and molar heat capacity, it's typically joules per mole degree Celsius. So grams or moles, just two different ways to represent the amounts. This is something that occurs. We kind of get these discrepancies in which units to use, either specific heat or molar heat capacity. When you get into the higher levels, academic chemists versus like engineers. So, but all you want to do is just be cautious of the units you're given. If you're given the specific heat in grams, you're going to do mass times that specific heat, your unit of grams will cancel out. If you're given it as a molar heat capacity, you're going to want to convert your grams of whatever substance into moles and do moles times the molar heat capacity. All right. And again, all of these units can be changed. Right. The degrees Celsius is going to be pretty standard. It could be listed as Kelvin, but that doesn't mean anything because it's the change in temperature. But it could be joules, it could be kilojoules, it could be calories for energy, it could be grams, it could be kilograms, it could be moles for the amount. Either way, you can do any conversions as long as they're in the same units. You can work with it. All right. Now, chemical systems change their energy. There's three main processes. Heating, cooling, which is the temperature changes. We've seen these on our heating curves. All right. Phase transitions, those were the plateaus on the previous heating curve, but here's a pressure temperature diagram, just any time we change from one phase into another. And chemical reactions, right? And we know what the two common profiles look like. Activation energy, if the products are lower, it's going to be exothermic. If the products are higher in energy, endothermic. All right, now, energy must be transferred to a system to cause a substance to melt or boil. All right, so I had a really smart group of kids once upon a time, a couple years back, and their sample of water just would not boil. Right, you needed to get a beaker of water boiling for the lab, and everyone else's was working, and theirs wasn't working, and they could not figure it out, and they were very upset. And it turned out they never plugged in their hot plate. So it was not on, it was not transferring energy. All right. So a watched pot never boils, but an unwatched pot always boils over. Funny joke. All right. The energy of the system increases. So that's why these phase changes, especially like boiling, it's a very long line on our heating curves. It requires a lot of energy to get that phase change to occur. Now, this is interesting. So it's saying likewise, a system releases energy when it freezes or condenses. We've already established freezing as exothermic, but it's still just kind of weird. But in a freezer, if you put a tray of ice into a freezer, as that water freezes, it is releasing energy into the surroundings. And the way the freezer is working is it's constantly pulling the energy out of the air, all right, by having really cold coils that are making use of an evaporator, right? So it's using the process of evaporation to pull energy away, all right, to take in the energy. And that first law of thermodynamics. So because the freezer is constantly taking energy away, that energy has to go somewhere else. And that's why you have vents on the back of the freezer typically, or sometimes on the bottom, where you would feel like a soft heat coming from. So like you never really want to leave like soda, let's say, next to the refrigerator, because there's heat coming off the refrigerator so that it can keep it cool inside. All right. Now, the energy absorbed during a phase change, it's equal to that amount. So we have the heat of fusions and the heat of vaporizations. All right. They'll oftentimes be called the latent heat of fusion, the latent heat of vaporization. But for these different substances, it tells us how much energy we need to get that phase change to occur. Typically, vaporization is higher in energy than the fusion, right? Solid to liquid. Now, the enthalpy change of a reaction gives the amount of heat energy released. So here's an example of a combustion reaction. C3H8 plus 5O2 forming 3CO2 plus 4H2O. In the diagram, we can see it's exothermic, right? Reactants are associated with a higher energy than the products. And it's telling us 2,220 kilojoules are emitted. So there's two ways we can write this reaction. We can do C3H8 plus 5O2 yields 3CO2 plus 4H2O plus 2,220 kilojoules, right? We can write the heat that is released as a product. Or we could just write the reaction as is and then include delta H. All right, so that would be the enthalpy change, and we would say delta H equals negative 2,220 kilojoules. It would be negative because it's exothermic, so it's saying this reaction has released that amount. All right, so typically we'll see it in that form. Typically we won't see heat written as a reactant or a product. We'll just be given the delta H along with the reaction. So here we have N2 gas plus 3H2 gas forming 2NH3 gas. Delta H equals negative 91.8 kilojoules. So for this chemical reaction forming ammonia, we have a negative delta H that tells us it's exothermic. So we might get a question like this. How much energy is given off when 222.4 grams of nitrogen reacts? All right, so we can just do our stoichiometry. We convert our grams of nitrogen into moles by dividing by the molar mass. And now we can set up a mole ratio. We would use the coefficient of the nitrogen, which conveniently is just 1, and we would put the negative 91.8 kilojoules up top. We got an answer, negative 729 kilojoules. The negative tells us that the energy is given off. If it was an endothermic reaction, we'd get a positive value. That would be energy taken in. All right, now, during a chemical reaction, bonds are broken and or formed, and these events change the potential energy of the system. If you can understand this graph, this will explain everything. All right, the idea that when a bond is formed, the bond is formed at a specific distance, right, between the two atoms where it's the most stable state. It has the lowest potential energy. So I want you to think, this is our bond. What's going to happen if we try to separate the particles? We have to go upward, right? We have to increase the energy. So this graph shows us that if we try to go upward on the graph just to get them separate again, we have to put energy in, right? Because they're going to be at a higher energy state. And then again, what happens when any two particles come together? It goes downward. So breaking the bonds requires energy, right? Energy has to be put in to break all of those bonds. And then when the atoms rearrange, when they form the new bonds, that bond formation releases energy. All right. So again, just keep this in mind. Energy is required to break the bonds, and then the energy is released when the bonds are formed. How much energy each of those steps take, that tells us if we're endothermic or exothermic. All right, so here's how we do the bond energy calculations. All right, the delta H, it's always the sum of all of the bonds broken minus all of the bonds formed. So the energy required to break the bonds minus the energy released. And as a result, something important to note with this, the bonds broken comes from the reactants, right? This is one of the only equations this year where we have the following order. The reactants have the bonds broken minus the products. So for these bond questions, it's reactant minus product. It'll always be the opposite for every other form we look at. So here we have hydrogen plus oxygen forming water. We have a lot of data on these different types of bonds. So like a carbon-hydrogen single bond is going to have an energy of 413 kilojoules. Right? A hydrogen-hydrogen single bond, 436. And then our multiple bonds are even stronger. So we're breaking two hydrogen-hydrogen bonds, right? So that's 436 each. We're breaking an oxygen double bond. That's 499. We are forming 4 oxygen-hydrogen bonds, 463 kilojoules each. So we would add up all the energy being broken. We would subtract all the energy being formed. All right. Now, that is looking specifically at the bonds. And one last thing I want to point out, you need to know what the structure is, right? Because you need to know what types of bonds are being broken and what types of bonds are being formed and how many of each. All of that's going to matter. Now, there's something else we looked at. There's something called the standard enthalpy of formation. all right? The delta H gets that subscript F naught, 0. So all of these reactions, they occur under standard conditions, which means that they use pure elements, right? All of these enthalpy of formation reactions, they're to make different compounds. They start out with the pure elements. They are always written in such a way so that the product always has a coefficient of 1, right? So it's totally fine to use half of a nitrogen or half of an oxygen molecule, right? So fractions are allowed in the balancing of these reactions, and those standard conditions, 25 degrees Celsius, right? And again, everything needs to be in its standard form, all right? So gas, solid, liquid, whatever standard form that substance would be in, but it's to make different products, all right? Nitrogen dioxide, NO2, has an enthalpy of formation of 33.18 kilojoules per mole. Calcium oxide, CaO, has an enthalpy of formation of negative 634, right? So we have long lists. But here's the equation. The delta H of a reaction is equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. So just pointing this out, this is products minus reactants. In the bond energy calculations, it's reactants minus products. So you just gotta be careful there, it's a little backwards. And we would include the coefficient of any reactant or any product, and any pure element is gonna be 0. But any compound will have a value associated with it. So if we were to do this first example here, sodium hydroxide plus HCl forming NaCl plus water, it's the products. So we would look up NaCl, that's negative 411. We would look up water, that is negative 241. We would add those. Because we get a lot of negative numbers here, it's very important to just, I would list everything in parentheses, do all of the products in parentheses minus all of the reactants in parentheses, all right? That's where you're gonna make a simple mistake with the math, just adding a number when you should have been subtracting it or vice versa, all right? The sodium hydroxide, negative 426, the HCl, negative 92, and I'm predicting that this is gonna be an exothermic reaction. Your products are gonna have a larger negative number than what you get from your reactants. All right, and this leads us to the last real big piece of Unit 6, Hess's Law. All right, so the concept of a state function is not required for the course. We visited this concept a few times. The state function is any process where it doesn't matter how you got there. It only matters where you started and where you ended up, right? So these energy paths, it doesn't matter how many detours we took. It only matters the final energy change. But Hess's law should be understood. So Hess's law allows us to use multiple reactions to come up with a new overall reaction. So I'll come back to the slide. So let's say we had this reaction, carbon dioxide plus methane forming CH3COOH. We can form it by adding up other reactions where we know the heat of formation, the enthalpy change, and we can kind of cross stuff out until we get the overall reaction. So these are kind of like puzzles. You piece them together. Here, we're adding these three up. If something shows up as a reactant and a product, it can be canceled out, and we end up with an overall reaction. So here are the rules for applying Hess's law. The first rule, when an equation is reversed, the value of delta H must also be reversed. So you're given a couple of reactions to play with. If you need to flip one around to get a certain substance as a product maybe, and you have it as a reactant in one reaction, if you flip a reaction, you have to reverse the delta H sign. So if it was negative, now it's positive. The second rule, any formula that is canceled from both sides of the equation must be identical, even in the same physical state. So you cannot cancel an H2O liquid with an H2O gas. They have to be identical, same state, everything. All right. And the third rule for Hess's law, if the coefficients of a reaction are multiplied or divided, the value of delta H must also be multiplied or divided by the same factor. All right. So let's say you have a reaction and it produces one product and you want two of those products in your final reaction, you can multiply that whole reaction by 2, but now your enthalpy change, let's say it was negative 100, you now have to multiply that by 2 as well. So it'd be like negative 200 in that example. All right, so that is Hess's law. That's really the last piece, and here's our last slide. When the products of a reaction are at a different temperature than their surroundings, they exchange energy with the surroundings to reach thermal equilibrium. Thermal energy is transferred to the surroundings from the products of an exothermic reaction. Thermal energy is transferred from the surroundings to the products of an endothermic reaction. All right, this is important. When we do chemical reactions that release energy, typically combustion, that heat is going to go somewhere. In a lab, it's very important that we can measure that heat. So in a lab, the heat from a combustion reaction, we will transfer to a source of water. All right, so the change in temperature of water, we can measure the delta T with a thermometer. We can know the volume or the mass of water we start with, and we know water's specific heat. So it's important when we do a reaction that we know is going to release energy, we have that water there to be able to like get an idea of what's happening. So we can see the change in temperature of the water. We can calculate the Q for the water, and that amount of energy gained by the water is the same amount of energy released by the reaction. Now, obviously, there's going to be massive percent error here because heat is also being transferred just to the surroundings in general, so we're not capturing all of it, but this is going to be a typical lab setup. This is actually a diagram from a former AP exam, all right? So that's going to happen. And if we're ever doing a reaction that's going to get colder, we're going to have a thermometer. We're going to record that change in temperature so that we can calculate the amount of energy a solution lost. And typically, a reaction that is endothermic will be happening in solution, and we'll just assume a specific heat of 4.18 for that solution. All right, so that is Unit 6. That is thermodynamics. Some important things. Delta H, negative, means exothermic. If you're looking at a situation and you're trying to determine if it's endo or exothermic, define the system, define the surroundings. Heat moves from hot to cold. Energy in, energy out. Think about which way it's going. That'll help you define it. And when you're doing energy calculations, if you're looking at bonds, it's bonds broken minus bonds formed. The bonds broken come from the reactants. The bonds formed come from the products. So that one seems like reactants minus products, whereas the other main formula, it's the enthalpy of the products minus reactants. And that formula, products minus reactants, the enthalpy change, the heat of formation one, this specific formula is on the reference. So you do have this, you don't have to memorize it, but just remember it's products minus reactants, except when it's bonds, in which case it's a little bit backwards. All right, so that should get you through it. All right, that is Unit 6. Best of luck.